There's a lot of things an aerospace engineer does. With every single project, an aerospace engineer starts with software and moves to hardware. So software is anything you do on a computer, any applications you use, any simulation software, design software, everything you do on a computer is software. And hardware is anything physical, something you can touch with your hands, anything that you're doing with your hands, maybe you're sawing something, you're gluing something, all of that is hardware. Building something in real life just comes out of spectrums. There's some things that are really, really software, and there's some things that are really, really hardware. So right now on the screen is a list of all of the things we're gonna talk about today. So starting from the software side, we have CAD, which stands for Computer Aided Design, and then we have FEA, Finite Element Analysis, CFD, Computational Fluid Dynamics. I know these all sound like really, really big words. I'm gonna make them a lot simpler for you and talk about what everything is later. But continuing on, we have Computer Aided Manufacturing, or CAM. So this is when we're shifting from stuff we're doing from the software to something we're doing with our hands. CAM is kind of in the middle where we're using something on our computer to do something else in real life. We also have 3D printing, composite manufacturing, and general building practices, machining, and electronics. Let's talk about our first topic, which is CAD, which stands for Computer Aided Design. So what is this? Basically, every object you look at, if that's your computer, if that's a mouse, everything you use and have was designed inside of CAD. CAD is really what's behind it all. What CAD is, it's a really powerful computer tool that allows you to 3D model whatever you're thinking of on your computer before you actually make it. There are a lot of methods of doing this. CAD is a very creative software. You can do a lot with it, but you can design a plane in it. You can design a cup. You can design anything you want and convert it to something 3D printable or something you can make. The next thing, right after you've designed something, you have to know if it works or not. And to do this, one of the things we use is called FEA, or finite element analysis. A lot of the time, you want to know how strong something is. So on the screen right now, I have an example, which are rocket tail fins. So first, I would design the tail fins in CAD, Computer Aided Design, and then I would bring it into FEA to make sure that it's strong enough. So over here at the very left is something called a static simulation. A static simulation is basically pretend you have an object and you're pushing onto it really, really hard. And a static simulation finds out if your object is strong enough or if it will break. Another thing you can do with finite element analysis is a drop test. So for my rockets, something that happens is that the rockets will hit the ground really, really quickly. And you want to make sure that when it hits the ground, it's not going to break. So using the same type of software, you can also test the impact with the ground using something called a drop test. And that allows you to make sure that, for an example, rocket tail fins don't break when it falls, or maybe if you have a car and you crash into something, you make sure that it's not going to break or damage the internals. So that's something else you can do with finite element analysis. So the last two tests I just spoke about, the static simulation and the drop test, are to make sure that your part is strong enough. But something else that's really, really powerful about finite element analysis is that you can also use it to make even better designs. So something here, one example of this is called topology optimization. And this here is an image of a topology optimization. How this works, you give it a 3D object, you tell what forces are applied, how it's connected. You basically tell the computer how you're going to use the object, and the computer will tell you what material is needed and what material is not needed. So this you see here is the output. All of the yellow area means you really need this material, and all of the blue area means you don't really need this material. What this allows you to do is design really cool looking shapes like this, which are really, really efficient. This right here, for an example, is a drone frame, and this doesn't look like your typical drone frame because there's all of these curves, all of these random holes, and the position of these holes are really, really optimized because of finite element analysis. That allows this drone frame to be only 70 grams when normal drone frames are almost 600 grams. And the next software we're going to talk about is CFD, also known as Computational Fluid Dynamics. So this is a very, very complex topic. All of these softwares are very, very complex, but this is specifically complex. What computational fluid dynamics does is that it simulates aerodynamics. That might also sound really complicated, but let me break it down. Basically, if you imagine you have a plane, there's air going over the plane, and you want to know how the air is going to go over the plane, and you want to know how the air going over the plane affects how much drag that's creating, how much lift that's creating. Anything to do with moving air and aerodynamics, you use computational fluid dynamics to do that. It makes a mathematical model of air pushing onto this wing in the middle. And all of these things around it show you how the air is going to move. Something special about fluid dynamics and aerodynamic testing is that unlike finite element analysis, which is very accurate, computational fluid dynamics can be slightly less accurate sometimes. So a lot of the time, what engineers will do is that they will use something called a wind tunnel. The problem with the wind tunnels is that they're very big and very expensive, and they're also very, very hard to get access to, which is why you might want to use computational fluid dynamics instead, which is less accurate but a lot more accessible. Next, we're going to talk a little bit about CAM, or computer-aided manufacturing. Basically, what this is, in engineering, you use a lot of metal tools, such as like a lot of machinery. To code those machinery, you use something called CAM, this computational aided manufacturing. What this does is that the software automatically creates Z code, which is basically the programming for all of the machines. The first step is to design your object. After you've designed the object, you're going to test the object using CFD and FEA. Once you're done testing the object, you have a final really good design. With that really, really good design, you want to make it in real life. And to make it in real life, you use CAM. CAM allows you to program machines to make it in real life, and then the machines will make it after. So it's this entire process that's really connected. CAMs, there's two types of CAMs we're going to briefly talk about. These two images show CAMs for CNC. CNC is basically any type of metal. So how this works is that it simulates how your extruder, how your mill will be moving around your object on the CNC machine, and that allows you to program the machines that you'll talk about later. Another type of CAM is called a slicer, which is a CAM for 3D printer specifically. Put your parts into the software, as in it would generate the programming to use a 3D printer. So on the right here is the output of the CAM, and you can see, much like a 3D printer, how you have a lot of lines. You can see the lines inside of the slicer, because that's the thing that generates the programming for your 3D printer. So now we know a little bit about the software. I'm gonna go back to the beginning just to do a quick review. To this point, we have talked about all of the softwares, and after you're done with software, you move on to make it in real life. So once again, when you start making something, you have an idea and you want to make a 3D model of the idea. You use CAD to make your idea a 3D model. And now that you have a 3D model, you want to see if it's strong enough. And to see if it's strong enough, you put it into FEA, or finite element analysis, to make sure it's strong enough. If your idea is related to planes and you need to test aerodynamics, then you're going to use computational fluid dynamics, or CFD, to test the aerodynamics. And now that you have a finalized part that's strong and aerodynamically stable, then you put it into CAM, which programs the machines to make it in real life. A lot of the softwares have all four of these tools, the CAD, FEA, CFD, and CAM, all built into the same software. So what I use is called SolidWorks, which is a really great CAD software. So I will design in SolidWorks, as in I open up a simulation tab, which does the FEA and the CFD, as in there's SolidWorks CAM, which allows me to code my machines. And it's all built in together. And a lot of the time, you don't have to open multiple softwares. They're all a part of the same software, but they're just different tools all in one software. So that part was a little bit complicated because there's a lot of software stuff that an aerospace engineer needs to learn about. But the next part, we're going to talk about making things in real life. And this is probably a lot easier to understand. So the first tools that an aerospace engineer will use to make something in real life is called additive manufacturing, which you guys know as 3D printers. 3D printers are amazing because they're really easy to use, as they're also really quick. So there's three types of 3D printers. There's FDM, SLA, and SLS. FDM is just the normal 3D printer you guys will think about as soon as I say 3D printer. How a FDM 3D printer works is that it melts plastic and it'll basically paint a layer, as it will move up a little bit, as it will paint another layer with the molten plastic, and it basically prints it layer by layer. So over here is a boat printed by a FDM machine. So right here you can see that there's layer lines because the quality of FDM is not as good as the other options we're going to talk about. But the strength of FDM is that it's really quick and it's also really fast. Another type of printer is called SLA. This type of printer is a lot slower and a lot less strong than FDM machines and a lot more expensive. But the good part of this is that there are no more layer lines. There's no lines inside of your object. So you have a really, really smooth print. So if you're doing something like a rocket where the outside has to be really, really smooth, SLA might be a really good idea for you. How SLA works is that you have a tub of liquid plastic, and it's a very special type of plastic because when a laser hits it, a UV laser hits it, it's solid. So how this works is that you will have a plate that goes into the liquid, and instead of using molten plastic, you have a laser that paints one layer, and then it will move up a little, paint another layer, and it's now a laser that prints the part. And the final type of 3D printer we're going to talk about is an SLS machine. So FDM uses plastic, SLS uses a type of powder. So how that works is that you put a lot of powder. It's almost like sand, but it's like a plastic powder. As there's lasers inside that shine at a certain point, and once it shines at that point, it becomes a solid. So SLS, you can make a lot of different shapes. You have a lot of flexibility in the shapes you can make because the powder allows it to print basically whatever shape you want without needing supports. Just to review, FDM is normal. It's the normal type of printer you will think about. It's really quick, really strong. An SLA printer uses a laser and a liquid. It's less strong, it's slower, but it's really, really high quality. And the SLS machine gives you the most freedom in the shapes you can make. There's also other special types of 3D printers, such as that allow you to do metal printing. So this is still an emerging technology. There's a lot of different ways to do this. Some people are using lasers to melt metals. Some other companies are making printers with almost metal toothpaste that prints like a toothpaste-like 3D object, as you have to heat it up after. There's a lot of ways to do it. 3D printing metal is becoming an option now. And 3D printing metal is really amazing because metals have a lot higher heat resistance than plastic. So you can put metal prints into fire. It won't be as damaged as plastic prints. And also metal is a lot stronger. So metal printing is a new technology that's emerging right now. And here are two examples of really, really cool metal prints. So over here is a liquid rocket engine. And instead of needing to do a really, really complicated process, having to bend materials together, this entire engine was made all with a 3D printer. So that is really great because it's very, very simple to make. All you have to do, click one button, tell the printer, start printing, and it will do all of this itself. For a rocket engine, if you use plastics, that obviously would not work because the fire is going to melt the plastic. But because we can now do metal printing, this rocket engine works because it's now metal. And then we're going to talk about something called composites. So composites is a different type of material that's really, really useful and really, really strong. Basically, think about composites almost like a fabric. Every single type of composite starts from a fabric, and you put a fabric into a plastic. I'm sure everyone has heard about carbon fiber. Super fast cars use carbon fiber. So carbon fiber is a type of composite. Also, people are now making bulletproof vests, as that uses another composite called Kevlar. Kevlar is so strong that you can basically shoot at it and it won't break. And there's another type of composite we're going to talk about called glass fiber. A lot of the boats are made out of glass fibers. So the big advantage of composites is that it's very, very light. Carbon fiber, Kevlar, and glass fiber are all a lot lighter than metals, but its stiffness, which is a type of strength, is much more strong than metals. So it's a very light material that's even stronger. Carbon fiber is standard for composites. You see carbon fiber everywhere now. The reason for that is because carbon fiber is super, super light. Carbon fiber is lighter than glass fiber and Kevlar and super strong. Kevlar is good because there's sometimes that you need higher impact resistance, like a bulletproof vest, and Kevlar has slightly higher impact resistance, and Kevlar can also resist higher temperatures. And glass fiber is another material. It's very similar to both carbon fiber and Kevlar. However, it's weaker and it's also heavier, so it's not as good, but it's a lot cheaper because glass is a lot cheaper than carbon. So if you need like a cheaper option, you might use glass fiber. But all three are great examples of composites, which are basically materials that are stronger than metal, but lighter. Yeah, so once again, what a composite is, it's a fabric. You need to mix them with some sort of plastic to make it an object. So how would you really make it an object? So there's a couple ways to do this. The normal way, you would start with a mandrel. So what a mandrel is a object. So this right here is just a long tube made out of wood, probably. So what you would do, you would put the fabric over it, almost like you're putting clothes onto the mandrel. And once you've done that, so basically you would put carbon fiber over the mandrel. And once the carbon fiber is on this machine, this mold, then you put a liquid type of plastic called epoxy. So you put liquid on it, and then you leave it to dry. This becomes a plastic which has carbon fiber in it. And once you remove that, you have a really, really strong composite. And that process I just talked about is called layupping. So in this image, you see he's already put the carbon fiber on top of an object. And this is the liquid plastic I was talking about. What he's doing with the yellow paper is that he's trying to get a really, really even layer of the liquid plastic on top of all of the carbon fiber. As then you would leave that to dry, as that would become a normal carbon fiber object. There's some techniques to make this easier or prettier. This is something called a vacuum bag. Sometimes what people will do is that after you've done what's called a layup, which is you put the carbon fiber on and you put the liquid plastic on, you'll use a vacuum bag. You put the entire thing in a bag, you suck all of the air out. The vacuum bag basically gives the entire part like a really big hug, and that makes it a lot smoother. That doesn't actually change the strength, it just makes it look a lot better. There's something else called pre-preg, which is just another type of carbon fiber with the liquid plastic already inside of it. So this makes it a lot easier and a lot cleaner to do. All you have to do is just put the carbon fiber on an object, push it to shape, and leave it overnight, and it will dry. There's also different types of fabric that you can use. Not types of fabric, but ways that the fibers are aligned. On the left here is something called a plane weave. So you see there's carbon fiber lined up here and carbon fiber lined up here. So it makes this checkerboard shape. So that's the simplest way of putting fibers together, as that's called a plane weave, as that's very strong this way and that way in the two directions of the weave. However, if you pull it apart from the diagonal, it breaks really easily. So this is something called a twill weave in the middle. So instead of having a checkerboard, now you have little triangles almost. As this makes it a lot stronger in the diagonals. You can basically pull on the diagonal without breaking it. So this is just a better version of the plane weave, but it's slightly more expensive. So there's also unidirectional weaves. And if you look here, all of the fibers are aligned in the same up and down direction. So this makes sure that it is very, very strong in the direction of the fibers. So if you pull on it up and down, it's incredibly strong. However, if you pull on it to the left and right, if you stretch it out, it will break really, really easily. So if you have some applications that only need strength in one direction, you would probably use unidirectional. Basically, with composites, there's a lot of different options on what you can do with them. You can also make it automatic. There's other ways to do it, so you don't have to use your hand and push it all over the place, which can be messy sometimes. So one of the ways to do this is something called a filament winder. So this is an image of the filament winder. What this is going to do is it spins around as there's a machine that just moves around, pulling the carbon fiber everywhere. So this is the machine that does that. Something else you can do is put carbon fiber into 3D printing filament. So earlier I talked about putting carbon fiber into a liquid, but you can also put it into a solid plastic. Right here is my rocket tail fins, which uses a carbon fiber reinforced nylon material. So how that works is that carbon fiber has to be put into nylon, as that allows you to 3D print carbon fiber, which allows you to have a really, really, really strong material. The next thing I'm going to briefly talk about is assembly. So an engineer builds things. There's skills that you only learn from building things. Like there's ways to measure things, there's ways to glue things. There's a whole lot of just knowledge that you gain from building things, which really makes engineering really, really fun. Because with engineering, when you build things, you learn a lot of tips. For an example, it may seem like tape is a very, very simple thing, but in engineering, there's a lot of different tapes. So for an example, you start with your normal type of tape that you use to tape paper together. This is great for maybe taping some electronics together. It's a very basic type of tape. You might use something called electrical tape instead. And electrical tape is a really good insulator, and it's really, really strong, and it's made for high temperature electronics. So if you're trying to tape wires together, you might use electrical tape. If you're doing batteries, there's a special type of tape for that called Kaplan tape. If you're doing some heavier duty taping, like you're taping two parts together, you might use masking tape. If you want to do some heavy duty taping, but you want to be able to take it apart, you use blue tape, which is called painter's tape. As there's also duct tape for really, really heavy duty taping. As there's also double-sided tape if you want to tape something light on. And if you need double-sided tape to hold, there's something called Gorilla double-sided tape. So something as simple as tape, there's so many different options in the world of engineering. As you build things, you're going to learn a lot of random things. Some things that seems really simple have a lot of endless possibilities. So even with something as simple as tape, right now there's 8 different types of tape, all for different purposes. Next, we're going to talk about machining, which is one of the things that a lot of people use to make an object really quickly. Machining is an umbrella term for all of the machines used to make metal parts. So from the left, there's something called a mill here. So how a mill here is that there's a really quick spinning drill over here. It's almost like a massive drill. So you would attach an object here. You can drill a hole in. You can do a lot with a mill. What you should remember is that a mill spins really quick. You can put a massive drill bit on the mill. Something else you can use is a lathe. How a lathe works is that instead of spinning your bit, your entire part's spinning really, really quickly. So this is the end of a lathe that attaches onto the part over here. And this thing would spin really, really quickly. That would allow you to make circular objects. So for an example, a rocket nose cone is a circular object. That is something you would make on a lathe. Something else you could use is called a water jet. How a water jet works is that this jet will spray water at speeds faster than sound, as that creates a laser of water, and that can cut an inch thick of steel. So over here, you see little cuts being made by a water jet. So a water jet, great for making 2D cuts in a big plane of material, and it's really, really quick. As in, the previous 3 things we spoke about are all somewhat manual. You have to be right next to it. The next thing is called a CNC machine. What a CNC machine does is that it combines everything. It combines the mill and the lathe together, and that can make a lot more complex shapes, and that can move all automatically. You don't have to move it around yourself with your hands. The machine will do everything for you. So a CNC is an automatic machine that combines a mill and a lathe together. And for really complicated shapes, you would use a CNC machine. And finally, we're going to talk about electronics. So aerospace engineers also need to know a lot about electronics. So coding is something they need to do a lot. Also soldering. So I'm just going to do one last review of basically the process from the very, very beginning. So when you first have an idea, you design it with CAD. Now you have a 3D model and you want to see how strong it is. So you use FEA to see how strong it is. If you want to test aerodynamic properties, you use CFD. And now from CAD, FEA, and CFD, you have a really, really good design. And from there, you want to make it in reality. So you'll program a machine using CAM. And once you've programmed the machine, you can either use 3D printing to make it. You can use a CNC machine and machining tools to make it. If you don't want to use 3D printing and machining, you can also use composites to make a really, really strong part. So now you have 3 options: 3D printing, composites, and machining to make your part. Once you've made your part, you're going to assemble it together and build whatever you're building. As in, you would do the electronics and put everything together. And that's basically the process of building anything.